So, ladies and gentlemen, the next lecture in our lecture on soil erosion is the rainfall erosivity or rainfall erosivity factor. And I would like to show you how it is calculated and what is the physics behind the rainfall erosivity factor. So what you see here is our example we want to work at. This is Bavaria, and the next pictures will always be shown with the situation in Bavaria, in Germany, a state of Germany where the famous football club Bayern München is. Munich is somewhere here, and this is Bavaria. So, how can we calculate rainfall erosivity? First of all, where is it used? It is used in the universal soil loss equation, USLE, sometimes called, where the soil loss in tons per hectare and years is calculated as a factor: the rainfall factor, the soil factor, the slope factor, the length factor, the coverage factor, and the protection factor. These are the factors which are in the universal soil loss equation. They distinguish or they divide up the full process in some sub-processes, in the processes belonging only to the soil, the processes belonging only to rainfall, to slope of your country, and so on and so on. So, and today we would like, or I would like to look at rainfall erosivity. The most important thing in rainfall erosivity is this picture here. It's the rainfall, the annual rainfall here in Bavaria. So you see the annual rainfall, and we should think that there where there is a lot of rainfall, there should also be a large erosivity factor, and this is what we want to have at the end of the day. Lot of rainfall, a lot of erosivity factor, and here in Bavaria we have a lot of rainfalls, of course, in the Alps. These are the Alps, and this is a Bavarian forest. We have a lot of rainfalls in this countrysides or in these areas here. Again, excuse me, oh no, this is the annual rainfall in Bavaria. As I said, here we have the Bavarian forest, here we have the Alps. Here we have a lot of rainfall, and in between the rainfall is quite low. So here also the rainfall erosivity should be low. So and the question is how to calculate the rainfall erosivity factor, or how is the rainfall erosivity, which is here, connected to the annual rainfall in a country. Yes, and I should say that there is no direct correlation between these two things, but they are belonging together. And we will see at the end of the day that the rainfall erosivity factor is mainly dependent on how the rainfall comes down through the year. So are there very strong rains, or are there a lot of smaller rainfall events? Is there only something like humidity of the air, that rainfall does not take place, but we have a quite humid air? This is the main question. It is not directly proportional to the rainfall. The rainfall erosivity is not direct proportional to the rainfall, but there is a certain relation between these two properties. So the first question what we have to answer is, what is the cause? What is the reason for rainfall erosivity? And physically speaking, rainfall is something like some small bombs falling on the bottom, falling on the soil, on coverage like vegetation or something. And these bombs, when they fall directly on the sand or whatever, then they start to erode the bottom. And the question is, how can we describe this process? And physically speaking, we have three options to describe this process. We can first of all think that it's the kinetic energy of a raindrop which decides whether it erodes the soil or not. The next thing is, from physics we know force, the concept of force. It could be the force which is acting through a raindrop on the soil, and it could be the force. And the third thing is momentum. Momentum, which is mass times velocity, which could be the reason for rainfall erosivity. And in the beginning, Wishmeyer and Smith, who are the founders of this equation here, Wishmeyer and Smith decided that it should be the kinetic energy. There's actually no physical reason for that, but they decided it should be kinetic energy, perhaps because energy is always the most well-known physical quantity, even for other scientists. When they think about physics, they normally think about energy. So I don't know whether this is correct. I doubt that this is correct, because we have also, for example, momentum. Momentum is kinetic energy, first of all, is mass of a raindrop times velocity square, and momentum would be something like mass times velocity, and not velocity square. And force would be something like the change of momentum when the drop enters the soil, when the drops reaches the soil and enters the soil. This would be force, the change of momentum. So what kind is correct, what kind of property is correct, I don't know, but they decided to take the kinetic energy. So unfortunately, kinetic energy is something like an extensive property. When we have more rain, we have more kinetic energy. And when we have less rain, then we have less kinetic energy. So kinetic energy is always proportional to the mass. So which kind of mass do I have to take here? One drop, the whole rainfall, or what do I have to take here? And the first idea always, when I have to look for physical laws, is to rewrite extensive properties which are dependent on the mass to an intensive property by dividing it by the mass itself or the volume. So when I divide it by the volume or the mass, then I get an intensive property which is not anymore dependent on the mass of, or on the amount of something, on the amount of rainfall. And in this case, I would like to divide the kinetic energy through the volume of rain. So this is the surface of the bottom, which I am looking at, and this is the rainfall height, the height of rainfall. In German it is Niederschlag, therefore it is an N where there is in English always an R. Here I take an N. This is rainfall. So this is the total volume on something like a surface. For example, 1 hectare, then I can take the rainfall height of a certain rainfall event, and then I divide the kinetic energy by this, and then I get something like an intensive property, meaning kinetic energy per volume. When I have more volume, then I have more energy. When I have less volume, then I have less energy. And this is the first idea, which is taken into account here. So then the next thing is, we should not take into account the kinetic energy, which should take the flux. The flux means how much kinetic energy goes through a surface. When I have, for example, here something like a surface and something goes through this surface, then we call it a flux. So how much of a quantity is going per seconds and per unit area through this unit area. This means that we have to take the flux. Phi is normally the flux, which is the rate of kinetic energy going through a surface per time. The rate of kinetic energy going through a surface per time. So for me, this is the most valuable quantity to describe something like rainfall erosivity when we start with kinetic energy. So let's look at this formula. When we now put an H here and DHN here and an DHN here, then it's the same formula. We did not change the formula because we put it here and here. We can cancel. Oops, excuse me. When we put an HN here and an HN here, then we could cancel it. So this is same expression for the flux of kinetic energy. So, but this first term here is nothing else than the kinetic energy density. As we have shown it here, this is the kinetic energy density, and this is the rainfall intensity. Die H Niederschlag, die H rainfall divided by the T is nothing else than the rainfall intensity. So the flux of kinetic energy is something like energy density times rainfall intensity. And this actually is the rainfall erosion factor. The rainfall erosion factor is always assumed to be proportional to the rainfall intensity and the kinetic energy density. Unfortunately, Wishmeyer and Smith in agricultural engineering, the rainfall intensity, the kinetic energy density is described as in capital E. So this is the rainfall kinetic energy intensity, and this is the kinetic energy intensity, and this is the rainfall intensity. E30 it is always called. I would like to call it .Hn, but in literature it is called I30, meaning that this is the maximum rainfall intensity in 30 minutes. This is by yes, this is by law. This is by law something like the rainfall erosivity factor. Yeah, the next question is, after we looked at the nomenclature in agricultural engineering, so the kinetic energy density is called capital E, and the rainfall intensity is capital I30, the rainfall maximum intensity in 30 minutes. Then we can calculate the rainfall erosivity of one rainfall event. This is the idea. So then we want to go to 1 year. The next thing is we have to go to 1 year. But first of all, I would like to show you how it looks like. The question is therefore, what is the energy density of rainfall? And there are a lot of theoretical and investigations and measurements on that. And it was found out that the rainfall energy density is dependent on the rainfall intensity. Here the x-axis is the rainfall intensity in millimeter per hour, and the energy density is this curve according to Wishmeyer, the black curve according to Wishmeyer and Smith, and there are a lot of other approaches. The red curve is an approach according to Mineo. All these approaches say that for very low rainfall intensities the energy density is more or less 0. Then it goes up to a certain point, and after a while, when we have large rainfall intensities, the energy density does not change anymore. It goes to a maximum, and this maximum is different depending on the approach you use. Normally, we take today the Mineo approach, which is the red curve here, because it's more smooth than the Wishmeyer and Smith approach. Here are the formulas for both approaches. So, and then we can introduce this in this equation, these formulas here, and we get the rainfall erosivity factor for one rainfall event. So then we have to multiply it by the rainfall intensity itself, and when we do this multiplication, we get this functions here. So here again the rainfall density, the rainfall intensity, excuse me, so in millimeters per hour, and when we multiply the energy by the rainfall intensity, we get something like these two curves, and these two curves are more or less linear, dependent on the rainfall intensity. So there's a linear relation more or less for larger rainfall intensities, there is a linear relation between rainfall intensity and this R factor for the universal soil loss equation. Only at small rainfalls the R factor is 0, because in this range here the rainfall is not able to erode soil, and this is a good thing. So when we have rainfall intensity smaller than, let me say, I don't know what it is, 15-20 millimeter per hour, then the soil will absolutely not be eroded. The next thing is, how can we go from one rainfall event to an annual rainfall? So, as I said, we have to distinguish between half an hour rainfall events. So what is the maximum rainfall intensity in half an hour? So this means that we have to take into account 1/2 hour, 2 half-hours makes 1 hour, 24 hours makes 1 day, and 365 days makes 1 year. So we have to sum up all these rainfall intensities over 1 year within 2 half-hours over 24 hours over 365 days. So this is a large sum. So if there is no rainfall in 1/2 hour, of course, then this h.hn is 0. And if there is any rainfall, then we have to take into account this function here and sum it up. So in the nomenclature of agricultural engineering, as I said, the rainfall intensity is a capital E, and the rainfall kinetic energy is a capital E, and the rainfall intensity is a capital I. So this is just the difference between my formulation and the other formulation. So when we do this, something like this, then we get the rainfall erosivity during 1 year. So, and now I ask the next question, what happens when we have different kind of rainfalls? And I would like to show it with this slide and with this picture here. And for me this picture is very, very important. This picture is made for an annual rainfall of 500 millimeters per year. So everything what you see here, this is the annual rainfall factor, is valid for a total rainfall of 500 millimeter per year. So let me explain it in that way. When we have 5 rainfall events, super strong rainfall events of 100 millimeters per hour, so 100 millimeters per hour, 1 hour, gives us 500 millimeters per year. So 5 rainfall events with 100 millimeters per hour. Then we would get, according to this formula, something like a rainfall intensity of 100, I don't know what, 60, 158 or whatever. When we have, instead of this, 10 rainfall events, which is here, of 50 millimeter per hour, 10 rainfall events 1 hour long with 50 millimeters per hour, then we would get, according to this calculation, something like a smaller rainfall intensity of 150 The annual rainfall would be something like 150. And when we would go to 10 here, no, 10 is too, when we would go to 25, we have 20 rainfall events of 25 millimeters per hour. Is it correct? Yes. 50, yes. 25 rainfall, 20 rainfall events per year with 25 millimeters per hour. Then we could go up here. Then we would have something like a rainfall factor of 125. And when all the rainfall events, when we would have rainfall events of 5 millimeters per hour, then we are somewhere here. Then we are somewhere here, and we sum up over 100 rainfall events with only 5 millimeters per hour, then we would have no rainfall erosivity. So the rainfall erosivity is not directly coupled to the annual rainfall itself. It is coupled, it is in a complex way coupled to how the rainfall comes to Earth. Are there a lot of small events, or are there some large events? And in that way I would like to do this simulation or this calculation, and then you can see what is your annual rainfall erosivity. Yeah, this is 500 millimeters as I said. So therefore the rainfall, the annual rainfall erosivity is not directly coupled with the rainfall factor. For 500 millimeters per year it could be between 0 and 160. Everything between 0 and 160 could be the rainfall erosivity in this area. There are, of course, when we don't have any climate changes, which is actually not the case, then perhaps we can parameterize this annual rainfall erosivity, for example, with such an approach. There are a lot of approaches how to get from the annual rainfall rate the erosivity factor. This is one example. There are a lot of other examples, but when the characteristic of rainfall changes due to climate change, then also this relation would change. So this relation is only valid for a certain area. And as you can see, of course, there is a relation between annual rainfall and the rainfall erosivity, but it is absolutely not straightforward, and you have to calculate it in the best way from a data set, having such an amount of data that you take this kind of data sets with such a lot of data, and then you can introduce this in this formula and in that formula or that formula, and then you can calculate for a certain area the exact rainfall erosivity with your data. Thank you very much.